Well, not yet. Okay. Now we're approaching the final session of the symposium. In this session, we have 3 talks scheduled. The first is by Konstantin Vergun. Are you here? He will be online.
Yes, I'm here. Good
Okay,
afternoon.
Konstantin, please share your presentation with the session. Okay.
Just a moment.
The second talk is by Igor Babin. Igor? Yep, thank you. And last but not least is by Ostap Vinyavsky. So we'll be there. You promised. Okay. So we're in schedule. Yes, we are. So I'm happy to introduce Konstantin Vergun, who will be talking on optimal solver selection for image matching. So Konstantin, please go ahead and take the floor.
Thank you very much for the introduction. I hope you can hear me well.
Yeah, it's okay.
Thank you. So good afternoon, everybody. Thank you very much for coming for the talk. And first of all, I want to apologize for being able to be here offline, and thank you for the opportunity to present my research nevertheless. And my topic is optimal solver selection for image matching. Okay. My name is Konstantin Vergun, and I'm a second-year master's student here at UKU. And I work as a principal software engineer in computer vision machine learning group at Logitech, where I make different things for intelligent conference cameras, which makes the topic of my research also highly adjacent to my professional interests and experience. And the advisor of this research is James Pritz, a computer vision professor here at UKU. And I want to express the gratitude to James for guidance and overall inspiration for this project. The plan of my talk is the following. First of all, I will talk about what is the image matching problem, how do we approach it, provide the related work analysis. Then I will outline the research gap and research questions, present our approach to solution, and outline current results and challenges in this project. So the image matching problem is a widely studied problem of computer vision. It is an essential part of different more complex tasks as 3D reconstruction, SLAM, autonomous navigations, and many more. And the input is 2 images of the same scene, and the output of this problem is expected to be a fundamental matrix, which describes the relation between the geometry of 2 images. So from the mathematical perspective, the fundamental matrix is the 3x3 matrix of rank 2, and it describes the transformation from first image coordinate space to the second image coordinate space. And it encapsulates both intrinsic parameters of the camera, such as properties of distortions and other image formation properties, and extrinsic parameters, such as rotation angles, rotation matrix, and the translation vector. Usually, this problem is approached by applying the pipeline of steps. Each of these steps has its own variety of methods which can be used. So first step is the key point detection for each image. Then these key points are matched across 2 images. And then since the fundamental matrix usually requires much less data than much less key point matches than there are available, then some sample of key points matches is selected to form the system of linear equation, which is then solved to obtain the fundamental matrix. And then this fundamental matrix is evaluated across the whole set of our matches. And in ideal world, there will be a single and precise solution to the system of linear equations, which will determine the fundamental metrics, and it will be the same despite what subset of image of points matches we take. But in reality, it's not the case. There is no precise solution to the system of linear equations, and there are different factors. First of all, because of the nature of data formation, which this system is based on. So this image discretization, it introduces some numerical errors and so on, and then the formation of the system relies on some previous steps, which might also be not ideal and have some inconsistencies or incorrectly matched points, for example. And so there is no precise solution. So we approach this as finding a solution of f, which minimizes the norm of a times f. And there is a question how to deal with the fact that this solution will differ depending on what subset of matches we will take. And it is usually tackled by applying the RANZAC framework, which is the method to iteratively sample the measurements, produce an estimation of, in this case, fundamental metrics, and then choose the result of fundamental metrics, which matches as much points in the original data as possible. So RANZAC is a pretty well-known and widely researched approach. It's pretty old. It was introduced in 1981, and it has a lot of different variations. So first of all, why might we need variations of this framework if it's so universal? So obviously we might search for some better efficiency in the convergence. We might want some different trade-off between the speed of convergence of algorithm versus the certainty of the fact that we found the most optimal solution. Then we might want to have something more tailored to specific cases for different types of data. And what can we change here? So we can change the best model selection criteria. It can be based on different statistical reasoning. We might change how do we sample measurements for each next iteration. And we might combine different variations of RANZAC under one umbrella in a way similar how do we do in machine learning model and samples. So there is a number of variations. We will not dig into the details of them. The details are provided in the paper submitted for this symposium, but we are specifically interested in one kind of variations of RANZAC, so-called adaptive or hybrid RANZAC. So the limitation of classical RANZAC scheme is the fact that it is bound to a predefined specific solver. And by solver here, we mean this part of an algorithm, this black box, which takes the set of matches and outputs a single estimation of fundamental metrics. There are multiple different solvers. The most widely used and default approach is to use the 8-point solver. And there are also solvers chooses less number of matches from 7 to 5, depending on additional constraints we apply to the nature of the scene. There is plain and parallax solvers, and there are other possible solvers. And why might we need different solvers? We might have different constraints, and these different solvers might perform differently on different kinds of scene. For example, the 8-point solver, it requires the 8 points not to be coplanar. And what happens if we feed 8 coplanar points to the solver? It will not be able to uniquely determine the fundamental metrics, which makes this algorithm, the solver, not applicable for this case. So this is why the different adaptive RANZAC schemes were introduced. For example, the DeGanZac scheme is tackling specifically the problem of coplanarity. So the idea is that on each iteration, the 7-point solver is applied, and then there is additional check. How coplanar is this currently selected subsets of points? And if they are highly coplanar, then additionally, the plain and parallax algorithm is applied, and then then fundamental matrix is obtained, and depending on which one suits better for the whole set of data, that fundamental matrix is selected to proceed. So this is conditionally applying a different solver. There are different approaches of so-called hybrid transect, which was introduced in 2018. So this approach uses two different sets of measurements, the 2D and 3D matches. And on each step of RANZAC, it applies two solvers, and it terminates once one of the solvers reached a specific so-called inlier ratio, meaning the measurements of how well does this solution fit the whole set of data. And based on this, we might ask the questions. So if we take a look at the hybrid RANZAC scheme, so if we, let's say, figure out that the solution provided by the blue solver is better. So the question is, did we really need to apply the red solver on each iteration? Or maybe we might have reached this conclusion much faster based on some logic. Or we can take it even further and say, and ask the question, would we be able to have some intuition whether this solver will be better for this scene and this solver will be worse for this scene? Because humans can make some kind of these kinds of conclusion based on prior knowledge. So this is why we identify the research gap as that fact that hybrid or adaptive RANZAC schemes, they rely on online information only. So no prior knowledge about the solver behavior is used. Then the more sophisticated solver selection or sampling strategies can be applied to optimize the number of worse solver applications. And the stopping criteria is usually one size fits all, meaning that no trade-off, no room for trade-off between the conversion speed and the certainty of the result. And we formulate the following research questions. So first is how to accumulate and use prior information, solver performance on different scene types. Then which sampling strategies will improve the performance of the hybrid RANZAC schemes, and how stopping criteria and sampling parameters can be adjusted for different trade-offs between accuracy and speed, and can the generic metric of solver result quality be designed when the null ground truth is available. And the anticipated outcome of this project is improved, first of all, runtime performance comparing to the current state-of-the-art hybrid RANZAC, and to provide a single black box algorithm which would be applicable for a wider class of scenes without need to priorly select the solver which will be suitable for this scene. Our approach to solution is based on idea to introduce few additional steps into the classical RANZAC scheme. So first of all, to accumulate the prior knowledge about solver performance in different scene into some kind of a model. Then to assign some metric of expectation of succeeding for each solver for the current scene. And then after each iteration, based on the online gathered information, on online assessment, how did the solver perform on the scene, to update these metrics for each solver, and on each iteration to select one of the solver from a set of available solvers. So the main classes, the main types of work to be done in the scope of this project is to prepare the infrastructure for experimentation, then it's data collection and preparation. And based on that, the offline model development and the sampling strategy refinement. So the timeline is on the slide. So for now, we have concluded the preparation of infrastructure and made some of the dataset preparation and starting on the sampling strategy refinement, and model development. So our evaluation of IDEA will be in the following settings. So we will be, our target would be to form a data set which has both planar and scenes with high depth disparity, and we want to make sure that our single black box approach will perform equally good on both of them. For the metrics, we will use the relative pose estimation accuracy. So it contains two parts: is degrees of rotation errors and the values of translation vector errors. And for the performance part, we will be using the number of times each individual solver was applied. So we plan to run the experiment with regular one solver RANZAC. We expect it not to perform well on whole data set, but only on one part of the data sets based on the solver which was selected. And we will be using hybrid RANZAC as a reference. And uniform sampling of two solvers will be used as a baseline for sampling method research. And then more sophisticated sampling methods will be applied. As for the data sets, so we have a requirement to have the wide range of depth disparities of scene. It should be enough to split into two parts, one for offline learning of the solver's behavior, and then for the whole algorithm evaluation. And camera displacement with intrinsics should be provided as ground truth for the data. We are targeting currently the image matching dataset, image matching challenge datasets. Specifically, we started from the 2022 dataset, since it directly has the rotation and translation as ground truth. And actually, a few days ago, the new image matching challenge has started, and I think that there will be more valuable data there. There are also some other smaller publicly available datasets. And initially, we'll be using the artificially generated point matches, since we, on some parts of this algorithm, specifically for the sampling strategy, we are not actually interested in the content of the image, but actually only on the operating on the point matches level. Regarding the sampling strategies, so there is a baseline of uniform sampling, which is completely agnostic of everything we learned offline and agnostic of current performance of the solvers. Then the next step would be to introduce the sampling based on current success metrics of the solver, most likely to be based on inlier ratio. And then the more advanced sampling technique we plan to try is the Thompson sampling. So it provides a better trade-off between sticking to the solver which already we know that it performs well on the scene, and with exploration of the solver which behavior is not yet well known. So for now, we have related work analysis performed and investigated possible sampling strategies improvement. We have prepared the framework for experiments and have implementation of solvers we plan to use. The initial data preparation is performed, and baseline approach with the uniform sampling is implemented, but not yet properly evaluated. The next steps would be obviously to focus on next two big parts, the offline model development and sampling strategy experiments and evaluation. So as for challenges, obviously the main risk is the time constraints. So the next month will be decisive for this project completion time. And unfortunately, the experiment setup and infrastructure preparation turned out to occupy much more efforts and time than it was anticipated. Thank you very much for attention, and I'm happy to address any questions or comments. Thank you.
Questions, please.
Yeah, hello, Konstantin. Thank you for your presentation. I think not only me, but all other listeners are curious. What are the problems with your setup, and what are the details? Like, do you aim to measure wall clock time in your research? Like, what kind of constraint do you have?
No, I don't plan to measure the wall clock time. So obviously that's an obvious way how to measure performance, but since it's sensitive to the hardware and so on, we stick to the performance metric as the number of times each of individual solvers in our from our box will be applied. Since again, the solvers also might be implemented in different ways with different performance and so on.
So your implementation will be platform and language agnostic. You just will count iterations, yes?
Well, yeah, so implementation obviously will be specific to some language and some specific implementation of the solvers, but the metrics will be agnostic to the language. That's the goal, not to depend on these things.
And you plan to implement on Python or C++, like?
So for now, we work together with James in implementing this whole thing in a bit exotic stuff language, which is called Julia. And there was also already some initial implementations of the infrastructure, and we made some advancements in that.
Okay, I understood the problems. Thank you.
I do wonder what was the last name of this Julia?
Just Julia.
Yeah. So thank you for your talk. I have one question regarding, so you have the feature extractor, the key point detector that generates the key points that you will match later on with the modified RANSAC. Yeah?
Yes, that's correct.
Okay, what kind of extractor you will use? Like, is it defined or it's just like something black box?
So it doesn't. Well, we don't think it will have like a decisive influence on the outcome of the research. So we will like the first option will be to run something like SuperPoint plus SuperGLUE, which
okay,
we expect to be more like universal than other stuff.
Okay, just like my question was regarding the next one, like different feature extractors will generate different amount of key points,
Right.
which will cause different time that you will need to match them. So basically your algorithm will be tied into the feature extractor. So you will need to evaluate it end to end, or you will evaluate just like time spent per like 1K of key points to match, something like this. It's just like
yeah, so the target is to improve only the RANSAC iteration part. So we will be measuring only number of iterations and some characteristic of these iterations. And since the matching is done prior to that, we will not be measuring this thing.
Okay, got it. So and the last like thing to clarify. So basically, you expect to reduce the time that like the amount of iteration of solver to reduce the time of processing to match everything, keeping the same performance, or you expect to have some kind of trade-off in terms of performance. Like, what's your expectation?
Yeah, so there are, and yeah, this consideration was like covered in the research question, which were formulated like separately. So the trade-off investigation is one direction, and the reducing number of iteration given target performance is a different direction. So first of all, we'll be focused on just reducing number of iteration for target performance. And then as a next step, we will be investigating different trade-offs which can be implemented. We anticipate they can be implemented using different parameters of the solver sampling strategy we'll be using.
Okay, thank you a lot and good luck. in your research.
Thank you.
Yep.
Thank you for your questions.
Just passing.
Thank you, Konstantin, for your talk. I have a question which is a kind of continuation of the previous one. Look, that's somewhat strange objective to minimize the number of iterations because different solvers need different time to execute. So if you apply 20 times one solver, it can be faster than 10 times a different solver. So what's the purpose then?
Yes, thank you for your question. That is obviously correct. And we are looking in the settings of the hybrid or adaptive RANSAC configuration, where it is given that multiple different solvers are tried out. And we are targeting not just to reduce the number of iteration of some given solver, but we are rather trying to reduce the unnecessary number of iterations which were applied for a solver which we turned out to reject as the one who provides the worst output. So we want to faster select the optimal solver and not to unnecessarily run the one which output we will reject, if that makes sense.
Okay, I understand.
Oh. Again, one more question from me. You mentioned that you have a stage of pre-training your solver selector or like hybrid solver on the data, but I have missed how the training will look. What is the measurement? What do you train?
Okay, so since this step wasn't yet properly performed, for now I can only share how do we what are the ideas for that. So we will be applying a solver for a set of images, and we will have a result of the solver application. For example, in the characteristic of its performance on the scene will be, for example, the number of iterations needed to achieve a certain level of accuracy, or maybe top accuracy achieved for a given number of iterations. And these kind of metrics will be the ground truth will be the trained data will be fitting for.
Okay, and then how you will recognize one or another kind of scenes on your evaluation?
So that is the part we expect to be covered like automatically by the neural network, since the different solvers, so if we will in our first settings we will pick a solver which works well on non-planar scene and a solver which works well on planar scene. And if we have a data which is more or less strictly divided between these two classes, we expect that for one solver, the performance will be good on only one part of data and on scenes, and a different solver will perform well on different part of scenes.
And so you'll have a neural network who will classify scenes into several buckets and then select appropriate policy for solver selection. Understood?
Yes, something like that.
Thank you.
More questions? No. Oh, yeah. Rostislav?
I have just maybe one comment. This is the most crucial part of your work, and it's strange that you postpone these until the very end. What if it fails? These neural network classification.
Well, neural network, first of all, that is correct, and as I mentioned, it's the main risk for now. And the reason for that is not that we just decided to postpone, is because we need some infrastructure which is crucial for our experiments. And if neural network fails, of course, it might so happen. And we still have our second part, which is related to the solver sampling, which both of these parts we expect them to contribute to the improvement. So if it fails in our time frame of next month, then well, that's life, and maybe it will not fail in the next few months or so.
Okay. More questions? Thank you, Konstantin.
Thank you very much.
Our next speaker is Igor Babin. Please share your screen. Yeah, there's the microphone. Let's check it.
Hi everyone. Hi everyone. My name is Igor Babin, and I'll present our work on topic of image and painting through refinement of feature space. And it was advised by Roman Ryazantsev and James Pitts. So the plan for my speech is the following. I will formulate. Okay, yeah. So yeah, I'll describe task formulation and motivation for this task. Then I go through related work and our findings of ResearchGap. Then I'll review our proposed solution and how we would our data set for training and evaluation and our early results. So task formulation for image and painting is the following. We have image and binary mask for input. And our goal is to restore pixels where the mask is 1. And from this example, images to the left is the input, and these regions for visualization purposes marked in violet color, and to the right is our expected results from algorithm. And motivation for this, one obvious application of this to use in real life for photo editing, but from a research point of view, this task is interesting because it requires deep understanding of image structure, texture, and semantics. And one more interesting application of this is better pre-training for image feature extractor, because it was proved by another paper that pre-training image feature extractor on in-painting task is much better than on regular ImageNet classification. And so related work, first work from 2009 was SpatchMatch, first algorithm to solve image and painting. And it was done without any neural network, so we have iterative algorithm. In the first stage, we have initialization, where we randomly initialize patch correspondence to the same image, but we ignore regions which we want to restore. And patches could be some hyperparameter, but it could be 1 pixel. And then we have 2 stages. First is propagation, where we searched for better matches in the neighborhood, and random search to more explore inside this neighborhood. Moving to neural networks approaches, first noticeable result was introduced in Llama paper. Idea of this approach is to use a net-like model. So we have downscale and upscale encoder decoder, and inside this latent space we have novel FFC blocks, which tries to refine these regions, and in the same time not to forget outside regions. And novelty in these blocks is the following, that we use convolution inside the frequency space created by transforming features to this space, and that's allow this method to perform this convolution on a global scale with a global receptive field, which is essential for in-painting. But this method has limitation in the resolution, and the following work, Llama Refiner, proposed to like refine these features in inference time. So they propose to use low image features, high resolution image features, and to optimize features from high resolution image using L1 loss, and iteratively repeat this in inference time, and it helps them to achieve better results for high resolution images. And one more recent work is latent diffusion painting, which was introduced in a Stable Diffusion paper. They propose to use they reuse this approach to iterate to work in this latent space, but for this task they propose to use mask as condition, so they just resize mask to the same dimension as latent space and concatenate this with latent vector and do usual denoising process, and it allows them to produce independent results. And based on this related work, we formulate few research gaps. So firstly, most of the work, most of the networks tries to not to forget about everything outside mask. And the next one is learning in this latent space. So all the approaches before try to decode this refined feature vector to the pixel space and then apply losses. And one more gap is that there are no any ablation on how this latent space structure and how which operation we could perform on this, and the structure, how different ground truth features and damage. And our proposed solution is the following. So we have two stages as in Stable Diffusion. So we have autoencoder stage where we have just encoder decoder which tries to just compress image and then decompress it with minimal losses in image. And the next stage, we reuse this encoder decoder to create latent space in which we operate next. Also, we added a mask encoder because we wanted to reuse encoder which has 3-channel input. So we decided to use external mask encoder and to combine it somehow with masked image features. For now, we did it we just concatenated these features, but we planning to do more like ablation study. Maybe it would be in some way as a control net, which would guide this refiner part in the middle. And this part in the middle, we just reuse from Llama to have consistent comparison with them, but we would later iterate on maybe some another approaches for this. And different from others networks, we have this skip connection from mask features to the refined features. This allows us to transfer knowledge about image from these mask features to the refined. We combine them, and we argue that it would save information from mask features and just to refine the regions which we need to refine. And lastly, we have training objective. We argue that it's enough to train only in latent space because using MSE laws, because usually all the previous methods decode these features, and based on this output image, they use, for example, MSE laws adversarial loss and all the others semantic-based losses. And because autoencoder space already contains information about semantic, we argue that it would be enough to train this network. And to summarize our proposed solution, so we use autoencoder for first stage to create this latent space and freeze it after. Then we do refinement in this latent space, and we use mask encoder for inserting guidance. And moving to dataset, we will reuse standard places to dataset, and we will follow the mask generation strategy from Llama paper to be consistent in comparison with previous method, because we improve only the model architecture, and we want to have the following rules for data in which we train. And for metrics, we will use two standard metrics for this task. First is learned perceptual image patch similarity, or LPIPS for short. The idea of this metric is that we have ground truth image, we have predicted image, we use some feature extractor to extract some semantically meaningful information, and then we just calculate L2 distance between them. And one more metric is FID, French inception distance. We also have some network for feature extraction, but then we calculate mean, and we calculate mean between the whole features for each dimension of these vectors, and then calculate this amount. And for our early results, we already train this first stage for autoencoder. We reuse the same encoder from Llama, but it was initially trained not in autoencoder, so we retrain it to be autoencoder. Then we set up the whole pipeline and do first our training. And based on this training, we visually notice that we use only L2 loss in latent space as in diagram, and we notice that results in much better compared to results which we could get if we train only L2 using L2 distance in pixel space, because it's known that L2 in pixel space produce blurred result, but in our case we can see like nice texture, which promising results for our later experiment. But we don't have any metric comparison yet. So yeah, that's all. So thanks for your attention.
Thank you very much. Do you have questions? Yes, please.
Yeah.
Always usual.
Okay, thank you a lot. I have like a few questions. Like the first one, as far as I know, like before diffusion era, usually GANs were used for the impeding problem, and in that case, we were just generating the image in painted one, and then based on the mask, we were blending in. And you were saying that you plan to do refinement only on the masked part. Is it the same, or like you plan to do it like in other way?
We want to learn in this space and without this GAN approach. Only like we doesn't have blending. We already have this delta or refined features which we want to learn, and like we argue that it's possible to learn without discriminator here.
Okay, so basically you consider that your network will do everything by itself, like only in the area where it should, like, but like without additional, like the guidance through the additional like control net.
Yeah, we believe like restoring these areas is much simpler than like restoring and also like saving all of other information is easier for network. And
Okay, thank you. One more thing is like for like the target goal of your method is to create pre-train for the pretext task, or you want to solve like in painting itself, because like a bit context here. In paper of masked autoencoder, they were doing huge areas of the images were masked, and they wanted just to make good pre-training here. In papers where we're focusing on in painting, where masking not such a percentage of the image, like not 50%, to leave some context. So what's your motivation here? Because there's no like strict border between this task, or you're going with pre-training, or you're going within painting, because you need to learn context.
Our main goal isn't in painting. We want to make everything faster, but without dropping performance.
Okay, cool. So if you go with this, my last question is in painting, there is common issue of regular structures. Like we have a wall with bricks or like spider net. Do you have any intuition how you will address it, or you will just try as it goes and see what it will be?
In Llama paper, it was addressed by Fourier, so it really helps to restore such regions, and because of it, we will reuse this block with Fourier in our refinement, and like we believe it could address this issue.
Yeah, it should. Thank you.
Thank you. More questions? No way. Okay, thank you very much. Ostap? It's my pleasure to introduce the very last speaker of our symposium, Ostap Wieniawski. I will talk on high-quality synthetic human generation for advancements in human understanding tasks. Ostap, the floor is yours.
So yeah, today I'll talk on high quality synthetic human generation for advancement in human understanding tasks. And yeah, I want to start with some abbreviations that we'll encounter through the presentation. And so you will not be confused. So for Viton, we talk about virtual try-on task. SMPL and SMPL-X are both parametric human models, skinned multi-person linear and expressive. And expressive stands for expressive hands and faces. DDPM, denoising diffusion probabilistic models, and VIT, probably known for all of you, is visual transformer. So the outline is usual as for today. It's motivation, research gaps, related works analysis, research goals, questions, proposed methodology, objectives and plans, and some early results. So firstly, speaking about motivation, I want to start with that large-scale data sets really revolutionized deep learning. And it all started with ImageNet for image classification. But it has one big limitation, that labeling process is very time consuming for human annotators. And this problem is even more visible for 3D tasks. So gathering labels for 3D tasks like depth estimation or 3D pose estimation is even much harder on images for human annotators. As a motivating example, here is a problem of dense pose and labeling. This is a problem where you have to establish correspondences between pixels in the image of humans and some template mesh of human body. The users who annotated these data sets were provided with these images and then some multi-view renders of the same body part. So they had to select both point on the template mesh and point on the picture. As you can assume, it's very time consuming and it's also very sparse annotations. So that's like a motivation why we need some sync for 3D annotation better. Yes, and other motivation is that some 3D recognition task boosts it significantly from the synthetic data. It's, for example, optical flow estimation. And here I mostly talk about synthetic data from rendering engines. But recently, diffusion models were introduced, not so recently, but still, and they allowed very high fidelity generation of humans. And also, what's important, they allowed generation with high level of controllability, which will be important for our pipeline. So actually, what we want to do in this work is start with the labels, and from them, through the controllable generation pipeline, generate corresponding images, and in this way, establish a data set which can be further used for supervised learning. Yeah, here's like an example of humans which can be generated with diffusion models. You can see that they're quite realistic. Some unrealistic effects are still there, but it's much better than results from rendering engines, which we'll see soon. And the impact of this work is that it can be applied in multiple domains like virtual try-on, entertainment, education, or human activity monitoring. For our research goals, I formulated two: investigate approaches for high-quality controllable human generation and explore whether synthetic data from diffusion models can boost the quality of methods for 3D pose and shape estimation. To be more specific, here is like a downstream task I want to improve. It's a task of 3D pose and shape estimation, actually. And the goal here is to estimate a human 3D mesh from a single image. It's not estimated in a free form, so you don't estimate like a single vertex on a mesh separately, but you do this through the parametric model, SMPL, actually. And what's important about SMPL is that it decomposes shape, pose, and expression of human body, so you can control them in a separate way. And it's very important for this parametric model. And here are some results, how this looks. So you can see that that's a task of avatar estimation from a single image. For the related works, firstly, I wanted to review the data sets. So because I'm proposing a synthetic data set, I want to share what's already there from the real world data set or synthetic data sets from other methods. And first of all, it's needed to say that gathering ground truth 3D meshes is very complicated. And it's usually done in lab environment because you cannot measure a completely shape of human body. And for this reason, most data sets, they actually don't provide avatars. They provide only 2D or 3D human skeletons. And on this data, our avatar estimation methods are trained, which will, as you will see, will result in their poor performance. So as an example of such data set is 3DPV. They used some inertial modules which were connected to humans, and from video sequences of these humans connected also to the these inertial modules, they could gather 3D skeleton information, but they had no information for human shape. So that's like a limitation of current data sets. Another approach is synthetic data. It can be generated in some kind of game engines, but actually it's very limited in diversity and quality of renders. So to actually have a very diverse set of clothing, backgrounds, I don't know, lightnings, it's very hard and time consuming for the artist to do that. So, but on the upsides is that it has 3D mesh with SMPL parameters readily available. And as you can see here, we have one very large scale data set called Agora. It has ground truth avatar for all the humans in the scene, but it's not very good quality, and I believe we can beat this with diffusions. Talking about synthetic data from neural networks, it all started with StyleGAN human. It was like the first model to show that with generative deep models, you can generate high fidelity humans, but they had all the problems with GANs, and they also were very limited in poses, shapes, backgrounds, so diffusion actually beats them there too. And here is, I guess, the most important part is that diffusion models, with their introduction, we were able to generate high fidelity images of multiple objects and human as well. And very important part is that many control methods were implemented for DDPM. And most important of them is just like simply fine tuning with this control modality, or adapter-based methods where you don't have to retrain a large like stable diffusion model from scratch, and you can just train small adapter network on top, which will introduce the control into the model. And also one very important, which we'll talk next, is image-to-image translation. It's the one which exploits this process of diffusion, but instead of generating from pure noise, you have your control, noise it not completely, but to some point, and generate from this stage, and it can help you control your output generation. We'll see some results soon. Yeah, and with these methods, we actually see that high precision of control can be achieved. So one of the adapter methods is ControlNet, which will be used in the work. Multiple modalities can be trained for ControlNet, and you can see the results of the generation. It follows very well normal maps, depth maps, edge maps, segmentation, whatever. But it's mostly designed to be like a 2D modality, which is aligned with the image. The same we can do for humans. So we can start with the avatar, which you can see on the left, and you can render, for example, its depth map in the middle, or this is called dense pose part indices on the right, and it can be also used to control human generation. Here are some results. In the top row, you can see like last two cells are generations from dense pose representations. Yeah, and image-to-image translation, you can start with the render, and so there is no retraining at all, no adapter. It's simply diffusion model where you noise this initial render of avatar, but to some point, not completely, and start from there, and it recreates a human. On the limitations that you have to recreate all the clauses, all the environment, because it follows quite precisely, and you cannot generate like additional clauses, which will be like pretty wide compared to the avatar. So I guess the main research gap is that synthetic data from DDPM generation was not utilized to boost performance of this shape and pose estimation models. So that's what we plan to do in my work. And for the research questions is what are the best methods for generating labels such that they follow realistic human pose and shapes? This is important because human poses distribution is not simple. It's not simply sampling from Gaussian. It's something much more complicated, and probably it should be learned from data. How can a text caption also be consistent? Because we need to provide some text condition into the diffusion models as they were designed. So the second is we talked about multiple modalities. So which one is optimal and which one will provide best results? One more important question. And also, how can we combine the benefits of ControlNet as there are more diverse? They allow wide closing, for example, backgrounds, and also this image-to-image translation pipeline, which follows pretty accurately, but is very limited in what we can add to the generation. For the methodology, I propose a simple like 4-stage pipeline. Firstly, sample from this real-world distribution of labels. Secondly, generate through controllable DDPM sampling human data set. Train downstream model on the generated data, and iterate first 3 steps while we can to compare different sampling and controllability methodologies. Speaking of label distributions, we need to generate labels from obviously real world. but establishing it is problematic. What we are thinking of is to run existing state-of-the-art method for avatar estimation on large-scale data set and use its predictions as this prior at this distribution of human poses, but it comes with limitations that this model can have its own biases, and we will see this in early results. As for backup plan, we can also use some learned distribution of human poses in the form of like variational autoencoders. It's already done, but I guess it's not the best way, and there are multiple limitations there too. For controllability, we will not consider fine-tuning diffusion. It's too time and resource constraint, and we are too constrained. So we'll look into adapter-based methods, ControlNet on multiple modalities. And also we want to combine it with image-to-image translation, but only for refinement stage after ControlNet generated diverse output. Here's one example of where ControlNet can fail. After we render our avatar, we actually lose some 3D information. So clearly you can see here that this avatar is facing us, but the generated human is looking in other directions. So this probably should be filtered or fixed. Yes, for controllability, what I said previously, actually, multiple control nets, filter failed generations, refine with image-to-image translation, optional. If we will have time, we'll try to refine hands and faces in higher resolution. And generating large-scale data sets, currently we are looking into more or less 300,000 images. For evaluation, we'll train state-of-the-art architecture. It's based on visual transformer, and it's called SimpleRX, compare multiple data sets with these generated methods and try to evaluate on well-established benchmarks. It's more or less, we have some small data sets of 500,000 images where we have pretty precise avatars, so this can be done. For the objectives, some of them are completed already. We want to gather these data sets of images, label it with SimpleR, already state-of-the-art model, train on these labels ControlNet, then establish pipeline for generation, and finally evaluate on the downstream task. Early results, finally. SimpleR, we noticed that SimpleR introduces bias into labels, so it's not actually real-world distribution. It's mostly the problems with shape and camera parameters, because also this model has to estimate camera. And you can see here that the pose is pretty precise, but when we overlay it with input image, we see that shape is not consistent, and also we saw that it works bad with perspective camera, so it usually estimates cameras that is very far from the object, making it actually almost orthographic. So this will have to be fixed. And we also have ControlNet trained on two modalities. One of them is from the dense pose. This one was trained on the generations of segmentation model for dense pose, and it actually follows much more closely the condition compared to the avatars. As I said, avatars are pretty misaligned with the input image, and when we trained ControlNet, this effect leaked into generations. So when we started generating humans from such modality, they were also misaligned with the control. And here's another example. You can see this effect as well. So currently what we expect is that ControlNet on the dense pose estimation will work better. Yeah, thank you for your time. So maybe you have some questions.
Thank you very much. Questions? Okay. This is the process.
Okay, so thank you a lot. I have like short question. You mentioned that if you will have time, you will focus on refinement of like high frequency structures like faces and hands. So do you have any like ideas how you will manage this?
Yeah, thanks for question. It's a great actually topic to discuss. I have a plan to, so firstly, why it's done badly currently, because it's usually hands occupy a very small area on the image, and in this latent space of stable diffusion, the model cannot just reconstruct these high frequency structures. So it's best to do this in higher resolution so we can focus on hands specifically. The only problem is how we can blend the final results. So this can introduce some artifacts, and I already saw this effect. And as for the methodology, I think it's best to do through image-to-image translation. You can focus your high-resolution image on this small region of hands, and it provides, I guess, the best results for generating hands. But it will have some limitations, like we cannot generate glows, we cannot generate objects that the human is holding, so it comes with its own limitations.
And what about faces?
With faces, it's much simpler. There are lots of methods based on GANs or others which just focus on face and regenerate.
And how to keep the identity?
What do you mean by
Like,
identity?
we have the face of a regional person and we want to generate the new face like there.
We actually don't have this problem. We are generating from the avatars, so we don't care about the identity.
Okay, got it. So identity is not that important. Okay, thank you.
Thanks. More questions? Yeah, Dmitra? I'm passing.
Thank you. And yeah, I'm interested about responsible AI applications here. Is it possible to generate with this approach people with disabilities, with maybe different traumas, to make this method and those applications like more inclusive? Because as far as I understand, we are tied to structure of avatar.
Yeah, thanks for the great question. Actually, we are. So the avatar doesn't have some like already built-in approach to handle, I don't know, some amputations, for example. But I guess it's possible to do. So you just synthetically cut off part of avatar, like hand or leg, and you can introduce it. Also, for the other approaches, I guess like this human represents the silhouette under clothes. So sometimes some parts of like legs can be covered by white dress. So you'll not even see what's under there. And I guess it can handle such cases. But yeah, it should be considered, I guess.
Thank you. More questions? So now I'm proud to announce that we may start calling that the second day. So thank you to all of you for coming, being active, being proactive even. I mean, in terms of delivering good quality results at Just Masters Symposium somewhere in Ukraine. I do believe that the reputation, which is already quite high, I mean, for this event, will further grow after people see your publications. So as for the publications, we'll be approaching you in approximately 2 weeks' time. If there will be anything that will require any correction on your side. I would suggest that all of us take this request constructively, just because we have a common goal to make it uniformly looking, of good quality, in order to apply for international book number, which requires some uniformity in the submission. So thank you very much again. Enjoy the rest of the evening, and I wish you good luck. And very successful defenses of your diploma works. Say goodbye.